Hi, pre-calc students. We're going to take a look at a really quick lesson today on function transformations, and we've already done some transformations so far, specifically related to translating, right? We've moved left, right, up, down. Well, there's definitely some other transformations we can look at as they relate to transforming a function. So I'm going to start by graphing y equals sine x. And it's probably been a while since you've graphed this trig function here, but y equals sine x, what you might remember about it is that the axes are labeled in terms of radians, right? So we have pi and 2 pi here. And then the max height of the sine graph would be 1, and the lowest height would be at -1. So the sine curve starts at 0, goes up to 1, back to 0 at pi, -1, and then back up to 0 by the time we get to 2 pi. It's not a huge deal if you don't remember exactly why this is the way the graph looks, but certainly this will be something we explore later on in the year in terms of graphing some trig functions. So what I want us to do is take that parent function and think about, well, what would happen if we had in y2 3 sine x? And what would happen if in y3 we had 1/2 sine x? Now, I guess the way I've set this up, it's suggesting that you can type this into your calculator. If you want to try it on your calculator, just remember that you'd have to be in radian mode, and you'd want to set your x min to be 0, and you could actually type in for your x max 2 pi to clearly see what's happening here. For your y values, if you're trying this on the calculator, I would suggest going from -5 to 5, and that should be sufficient to see what we want to see. So I'm going to show you what this would look like. If you were to, let's say, type in 3 sine x, what's going to happen is you'll now find that the max height is at +3 and that the lowest height is down at -3. So it's still going to start at 0, but now you're going to go up to 3, back to 0 at pi, down here at -3, and then back to 0. So you're going to see this graph right here for something like 3 sine x. And then finally, the last graph, maybe you can even predict what's happening here. If there's a 1/2 out front, you're now only going to reach a height of 1/2. So it's going to come up to 1/2, back down to 0, down to -1/2. Okay, and it just looks pretty cool once you graph all these on the same set of axes. But just to get the idea of, hey, like what's going on when we put a number out in front of our function? And we're going to explore that idea in this example below. So go ahead and take some time here to think about what would the effect that this 3 has, right? There's a 3 in front of each of these functions, and we have the parent function x squared, radical x, cube root x, absolute value of x. So I'm going to go ahead and sketch those real quick. So we've got x squared. We should really know what that looks like by now, I think. Radical x, cube root x, and then absolute value is this v. Okay. If you want, hit pause, see if you can sketch in a different color or label it differently, what the transformation would look like if we put a 3 out front, because I'm going to sketch them right now. Okay, so what effect does that 3 have? Well, when I input values for x in any of these functions, the output y values are now tripled. So if you think about any of the y values on this graph, they're now going to be triple their values. So in the quadratic one, it's more narrow than the original. Okay, that's what 3x squared looks like. If I had 3 radical x, same idea, any y value is going to be tripled. So now it's going to just grow that much faster. In the example of the cube root function, it's going to become more steeply negative and more steeply positive on this side. And then for absolute value, you'll see a similar effect to what we saw for the quadratic. Your v is just going to be more narrow as when compared to the original. So in conclusion, what do we want to say here is that if you have something of the form y equals a times f of x, and I'll tell you in all of these examples, we're analyzing when a is greater than 1. The resulting effect here is that you get a vertical stretch of the graph, also known as a vertical dilation. So we're dilating this graph vertically in a sense. So what's happening is you're multiplying the y values by whatever a is. Okay? And you can see that stretching effect happen. It's like you're taking the graph and you're pulling it this way vertically. And that's what happens to those sketches. All right, moving on to the next set of examples. Same parent functions again. So maybe just go ahead and quickly sketch those. we've got y equals x squared, y equals the square root of x, cube root x, and absolute value of x. So you can see really quickly here, the only difference is now we're going to analyze, well, what happens if my value of a, that scale factor, is something like 1/2? It's very similar, right? The output y values are now going to be half what they were a second ago. So when I plug in values for x, if I think about what half the y values would look like in the quadratic, that's going to be wider than the original. For the radical function, it's going to be a graph that's underneath the original function radical x if I cut the y values in half. Okay, for the cube root of x, we're going to squeeze in a graph in between the branches of cube root x, right? Cutting those y values in half, it's now going to grow slower. And similar to the quadratic, the absolute value is going to be a wider opening when there's a 1/2 out front. Okay, so how do we describe the conclusion here? Well, we're still looking at something on the form y equals a times f of x, but I'm going to qualify a in this case as being between 0 and 1. Okay, so we'll talk about what happens when a is negative in a little bit, but for now, the a value is some decimal or fraction between 0 and 1. And the way you would describe this is it's a vertical shrink. Sometimes you'll hear the word compression as well, compressing the graph or shrinking the graph. It's still an example of a dilation. Whenever you multiply by a scale factor, it's a dilation. And you're still multiplying the y values by a. But multiplying the y values by a fraction is going to make this graph shrink in this way and push the graph in along the y-axis. Okay, so hopefully you had some good recall there about what dilations do to the graph. This is something you would have seen in Algebra 2. Moving on to the next page, look at those same old parent functions again. We're going to look at what happens when we throw a negative out front. All right, so go ahead and graph x squared, radical x, cube root x, and absolute value of x. So there's all my parent functions, and what we want to do is figure out what happens if we put a negative out in front of the function. And if you're unsure, again, type it into the calculator. Type in negative x squared, negative radical x, and see what happens. But I'll show you what these resulting graphs are going to look like. When you put a negative in front of the function, it's going to do that for the parabola. It's going to do that for the radical. It's going to do this for the cube root function, and it's going to do this for the absolute value function. So I'm hoping that as you're sketching those alongside me here, that you're thinking, hey, I know what transformation that is. And the conclusion is, if you have something of the form y equals negative f of x, so I want you to think of this as you're negating the outside of the function. It's like you're negating the y values. When you negate f of x, it's like negating y. So when you negate the y values, what that results in is a reflection over the x-axis. Okay, transformationally, negating y means reflect over x. And if you're being a really good guesser about this, I think you probably know what's happened in the last instance. But you know what? Just for good old times, let's graph these parent functions real quick. So we've got x squared again. We've got radical x. Boy, you're going to be an expert on these by the end of the unit. Okay. And when we take a look at what's the effect of negating x on the inside of the function, right? Before we were outside, now the negation's on the inside. What's going to happen in these instances is for something like the quadratic, well, it's a little weird, but it's going to be right on top of that old graph. That's a little tough to see. When I negate x in this example, it's going to go like that. When I negate x over here, it's going to look like this. And then when I negate x for the absolute value, it's right on top of it again, just like the quadratic. So when I think about the effect here, I think the one that's the clearest to see what's happening is probably this example here, isn't it? Because here they're right on top of each other, but maybe you already knew what happened. Here, this graph looks identical to this graph, so I'm not sure what really happens. But when I compare this situation with radical x to this situation with radical x, hopefully you can see it's pretty clear that negating x is going to flip it over the y-axis. So the last transformation is if you have y equals f of negative x. All right, and think of how this kind of connects to some of those symmetry things we've talked about. Okay, y equals f of negative x, which is negating the inside of the function. That's going to be a reflection over the y-axis. So I think it's pretty clear as to why the quadratic and absolute value won't really looks like nothing happened. Those already have y-axis symmetry. And because I'll say the cube root of x has origin symmetry, that's why reflecting over x and reflecting over y look the same. So that's kind of a unique case as well. But when I look at this radical example, that's pretty clear that we are reflected over the y-axis as compared to this example as to when we are reflected over the x-axis. And although I think students are pretty good with finding a negative and realizing that that's a reflection, it is really easy to confuse whether I reflect over x or reflect over y. So make sure you understand these concepts really well, because in the next lesson, we're going to apply all of the transformations at once: translations, dilations, reflections, and everything in between. All right, that's it for today. Have a great day.